Bismillah ar-Rahman ar-Rahim. Now, after we discuss the area problem, today we have something related to the area problem. We call it the definite integral. Okay. You remember the area problem? We said if we have a curve y equal to f of x, which is greater than or equal to 0, we have the x-axis and the y-axis, and we were defining what is the meaning of the area under the curve. First, we went through an approximation process. We define what we call approximating rectangles. We use the sample points sometimes to be the left points, to be the right points, the mid points, different type of approximations. At the end of the day, we define the area to be the limit as n goes to infinity of summation I equal to 1 up to n f of xi star delta x. We observe that now after taking the limit as n goes to infinity, the choice of xi star, you know, xi star is the sample point chosen to be between the sub-interval xi minus 1 up to what? Up to xi. We observe that at the end, the area, if you choose this point to be the right point of each sub-interval, or you choose it to be the left point or the midpoints, after taking limits, it will give the same answer. And that answer defined to be the area under the curve. Now, what is a definite integral? We defined the simple here. We said the integral from a to b f of x dx, we define it to be equal to the limit as n goes to infinity, I equal to 1 up to n f xi star delta x. Okay, to see what are the main points inside here, what do you mean by delta x, what do you mean by xi's. Actually, we start again by an interval which is AB. This is A and this is B. So what we do, we just partition this interval into sub-intervals. So we define delta x as before to be B minus A divided by N if we are shooting to get a uniform partition. Okay? So each sub-interval has the same length. Now, we define the xi star to be the points, again, the sample points in the sub-interval xi minus 1 and xi. Then we define this summation and the limit. Limit as n goes to infinity. Now, if this limit exists and gives the same value for any choice of the xi's, then this is called the integral from a to b f of x dx. If the limit does not exist, we say the function is not integrable. If the limit exists and gives the same answer regardless of the choice of the sample point, we said the function is integrable. Okay. We can see now this definition here. And the definition of the area look like the same. So, does it mean that the integral or the definite integral here from a to b f of x dx is the same as the area under the curve? That's one point here. If yes or no, if no, what is the difference between the definite integral and the area under the curve? Before I move to that point, I need to say something about the simple here. The function f of x, which is inside the integral here, is called the integrand. Okay? These 2 points are called the limits of the integral. So a is called the lower limit of the integral. B is called the upper limit of the integral. So what about dx here? Dx indicates that the integral is taken with respect to the variable x. So simply it says that the independent variable here is x and it's running from a to what? To b. Okay. So the first point we need to understand, what is the difference between the area under the curve and the definite integral? This is one thing. If there is a difference, what is the difference between these two? When the area will be equal to the integral, when the area is not equal to the integral. And then, what is the meaning of definite integral geometrically? Okay, that will be our next point. So let us see now what is the meaning of the definite integral geometrically. Before we do that, we have some notes about the definition here. Now, if you remove the limit, you end up with the summation from I equal to 1 up to n f of xi star delta x. Okay. Now the summation itself without the limit is called the Riemann sum, stands for the German mathematician. Okay. So the summation without the limit is called the Riemann sum. This is one thing. The second point here, if you restrict f of x to be greater than or equal to 0, so if all values of f of x are non-negative, in other words, then what does it mean the integral here? it ends up that the integral in this case is the same as the area under the curve. Okay, if you just graph it here, then we have the previous problem. We have the area problem. We have a curve y equal to f of x. This is the x-axis, the y-axis. This is y equal to f of x. And we have 2 points. We have A. We have the point here B, or the line x equal to B, the line x equal to A. It happened that now f of x is non-negative, always greater than or equal to 0. So we end up that the integral here from A to B, the definite integral AB of f of x dx, the integral from A to B of f of x dx is exactly equal to what? Is exactly equal to the area problem we defined before. So yes, if you look for the definition here, and you restrict f of x to be non-negative, then this definition represents the area under the curve. Is it always that the integral is the area under the curve? The answer is no. Let us see note number 3 here. If we have the function sometimes positive, sometimes negative. For example here, let us take a specific one, assuming we have such a shape like this, which is similar to the cosine function, for instance. We have x-axis, y-axis again. And let us assume that this is our starting point of the interval A, and this is the end of the interval, which is equal to B. Okay? Now, here, what is the difference between the area and the definite integral? Okay, for sure, this portion of the graph between the x-axis and the curve y equal to f of x, here, I will give it the name A1, area number 1, okay? And this area here, which is bounded between the graph and the x-axis, again, I will call it area number 2. And here I have it area number 3. Now, if someone said, what is the area bounded between the curve and the x-axis? Simply, the area is equal to what? The area here is equal to the sum of these areas, A1 plus A2 plus A3, okay? But, what is the definite integral from A to B of the function f of x? What is the integral of from A to B f of x dx? Is it equal to the area? The answer is, in this case, absolutely no. So what is it then? The answer will be, it is the net area. What do you mean by the net area? It means you need to sum up all areas above the x-axis. So A1 plus A3. Then you need to subtract from them what? Or you need to add to them, if you like, the negative of the areas below. So simply you are subtracting the areas below the x-axis. That's why we said the area is always non-negative, either 0 or positive. But the definite integral, it depends. You may have it positive answer, you may have it 0, you may have it negative answer. If the total area above is greater than the total area below, then the difference will be positive, so the integral is positive. If they are the same, for example, if you take an odd function and between minus a and a, so we are expecting the area below to be equal to the area above because it is symmetric around the origin, then the total or the definite integral will be 0. And you may have it positive or negative if the total area below is more than the area above. So what is the difference between integral and areas? We can say that the definite integral is not the area but the net area. So the difference is, if you have the function is not always positive, so the difference between area and definite integral, the definite integral represents the net area, but the area is the sum of the areas, okay? So that is the difference between the simple integral from a to b f of x dx and the area problem we discussed before. Now, what is our duty in the next point? The first one, we need to know how to approximate the definite integral, meaning how to find the Riemann sum by using different sample points. It is exactly as what we did before in finding the area by using approximating rectangles with different sample points. We did left point approximation, we did right point approximation, we did midpoint approximation. Same thing is applicable here. We can find the Riemann sum taking the sample points to be the right points, the left points, or the middle points. That's one thing. The second one, how to evaluate exactly the definite integral. And we will do the same process we did for areas, taking the limit, summation stuff, and etc. That will be our next point. Now let us see how to do two things. The first one, how to evaluate Riemann sum if we have a specific choice of the sample points and a specific number of approximating rectangles. The second one, how to evaluate the exact integral, the definite integral. So that will be done in the following exercise. It says evaluate the Riemann sum for the function f of x equal to x squared minus 2x. Now, he specified. He said taking the sample points to be the right endpoints. So I'm talking about Rn or R. In this case, it is R4 because he specified the number of rectangles. And we have the beginning of the interval A. We have the end of the interval B from 2 to 6. Okay, the number of approximating rectangles will be 4. So we are looking for R4. So what is the Riemann sum in this case? What is the Riemann sum? Riemann sum in this case, let me call it R4. So I'm talking about the right endpoints with 4 subrectangles. If we consider them like this is equal to what? We do the same steps we did before. So I need to calculate what is delta x. Then I need to form my sample points. Then I calculate this expression R4. So let me just erase this one and start again by finding these points we need. So I need delta x, the length of each subinterval. So it is b minus a divided by n as before. So it is equal to, in this case, specifically we have 6 minus 2 divided by n, the number of approximating points. So this is 4. 6 minus 2 is 4 divided by 4. That's equal to what? That's equal to 1. Now, forming the partition, so we can choose the sample points now. This is what we have. This is equal to 2. And this is equal to 6. And we need to form 4 points. So the next one will be 3. So this is 3. And the next one will be 4. The next one will be 5. So the next one will be 6. So let us say we end up here. So this is just to be consistent here. Okay? So this is the partition we have. We have 1, 2, 3, 4, 5 points and 1, 2, 3, 4 subintervals. He said use the right endpoints. The right endpoints means in the first interval I will choose 3. In the second one I will choose 4. In the next one I will choose 5. In the last one I will choose 6. So what is the Riemann sum? By taking 4 points, let us call it R4 Riemann sum, taking 4 sample points and the endpoints to be the sample points. So delta x is 1. So that is 1 times the summation now from 1 to 4. So that is equal to what? F of 3 plus f of 4 plus the next one is f of 5 plus the last one is f of 6. This is what we have. Good. Now let us calculate this. What is f of 3? We have the function here. We substitute. This will be 3 squared. That is 9. 2 by 3 is 6. 9 minus 6 is equal to 3. So simply this is equal to 3. Plus. Now we have 4 squared. That is 16. And 2 times 4 is 8. 16 minus 8 is 8. So that is equal to plus 8. Next, I need to substitute 5. Okay? X equal to 5. So this will give me 25. And this will give me 10. 25 minus 10 is 15. So this is equal to 15. Okay? Finally, I need to substitute by 6. So that will give me 36 minus 12, which is simply 24. Okay? Now you need to add these numbers. So what we have here is 15 plus 24, that is 39. 39, if you like, plus 3, that is equal to 42 plus 8. So this is equal to 50. Okay? So this number stands for the Riemann sum by taking only 4 subrectangles. Now the next part is how to evaluate the definite integral from 2, which is the beginning of the interval here, up to 6 of our function given here, which is x squared minus 2x dx. Now, what does it mean? What does it mean, the definite integral now? If you go back to the definition here, we can say that the definite integral is equal to, we define it to be the limit as n goes to infinity, and that is summation of I equal to 1 up to n. We said f of xi star, but I can choose the right points here, or the left points, practically, or any point in between, theoretically. Why? Because they give the same answer. I will choose here the right points. Meaning, I am forming here Rn, the Riemann sum with endpoints, and taking the sample points to be the right endpoints. Okay, what is the formula here? Delta x, as before, is b minus a divided by n. So, what is b minus a divided by n? It is 6 minus 2 divided by n. That is 4 over n. Okay? What are the xi's? The xi's will be as before a plus I delta x. Now, in this case, a is 2 plus I delta x. This is delta x. So, we multiply by I. So, this is 4i divided by n. That is the formula for delta x, and these are the sample points we have. Now, let us start the process of calculating or evaluating this summation and the limit, which is called integration or definite integral. Okay? The procedure of evaluating this expression is called integration. So let us evaluate this kind of expression by using the definition. Okay? Later we will have a nice tool called the fundamental theorem of calculus that will help us to evaluate such a thing in a simple way. But for the time being, we are doing it by definition. Okay? So how to evaluate this? Let us substitute. We need to evaluate the limit as n goes to infinity of the summation I equal to 1 up to n of f of xi. These are the xi's. We have 2 plus 4i over n. We substitute in the function there. So what do we have? Which is the function here, x squared minus 2x. So that will give me the following. It will give me 2 plus 4i over n all squared. I am squaring the values of x. Minus 2 times the xi's. 2 plus 4i over n. What I did now, I just took these numbers and substituted in the function. Now, everything here multiplied by delta x. Everything here, I need to multiply by delta x, which is simply 4 over n. Now, look. This is a summation that is running over I. So, I can't take this one outside the summation. I cannot take it outside the limit because it is dependent on n. But I can take it outside the summation here. So, simply I will say, this is equal to limit as n goes to infinity. I'm doing some simplification now. So I will take 4 over n first outside. Then I have summation here. I equal to 1 up to n. Now, you need to simplify this. So this will give you 4, the first one square, plus twice the first, the second. So it is 2 by 4, which is 8, by 2. That is 16 I over n plus the second one square, which is 16 I squared over n squared. Minus 2 by 2, which is equal to 4. Minus 2 by 4, that is 8i over n. Everything here is inside the summation simple. Okay? Another simplification here. Of course, now, this 4 will cancel with the 4 here, so we take rid of these two things. Then I have limit as n goes to infinity of 4 over n times summation of I equal to 1 up to n, summation of, now the cancelling 4 with the minus 4, you have 16i over n minus 8i over n. That is 8i over n plus what? 16 I squared over n squared. Okay? I recall now these two formulas that will be used now. Recall this. We have summation of I equal to 1 up to n, which is the same thing we did for areas. It is n plus 1 divided by 2. If we need to succeed always, these formulas should be clear. Okay? We have also summation I equal to 1 up to n of I squared, because we need it here. That is n plus 1, 2n plus 1 divided by 6. I will use these two formulas to simplify the summation stuff here. Okay? So what is next? What is next? The next point will be, see here, it is limit as n goes to infinity. I will keep this 4 over n outside, then I will open a bracket like this. Forget about 8 over n. We are summing over I. So what is the answer here? It is 8 over n times the summation of I. What is summation of I? It is n plus 1 dividing by 2 plus. For the next term, forget about 16 over n squared. It has nothing to do with I. I'm summing I squared. What is I squared? It is n plus 1 to n plus 1 divided by 6. This is what we have, okay, without summation now. We simplified it. Now the only thing we need to do is just to multiply and then take the limit. Okay. If you multiply and get the limit, observed here, if you multiply n by n, this will be n squared. You have the same power in the numerator and denominator. So we need to take the leading term over the leading term, okay? So what is that? It will be 8 by 4. The final answer will be 8 by 4 divided by 2. This is one thing, plus the next one. If we multiply n by n squared, we have n cubed. And this is something in terms of n cubed. So again, I will take the leading term over the leading term. That is 4 by 16, okay, by 2. That is the leading term of the polynomial upstairs divided by what? Divided by 6. That is the final answer. We need only to simplify things now. I have 8 by 4, which is 32, divided by 2. This is 16, okay. I can divide by 2 here. This will be 3. I divide by 2 here. This will be 1. So what do we have? 4 by 16, which is, that is 64 divided by 3. That's the final answer. The only thing you need to do is just to simplify by adding the two terms. So this is 3. This will be for sure 48 and multiplying by 16 plus 64. So the final answer will be adding these two numbers. So 4 plus 8 is 12, 2 and 1. So this is 1, 1, 2 divided by 3. That is the exact value for the definite integral given here. From 2 to 6, x squared minus 2x dx is exactly now equal to 1, 1, 2 divided by 3. When we did sort of approximation, we get the answer is 50. If you divide this, of course, it will be more than 50 because here we have some error. We are choosing only 4 subrectangles. But here, by this procedure, we end up with the correct answer, with the exact answer for the definite integral. If you do the same by choosing the endpoints to be the left endpoints, you will end up with the same value if you take the limit, okay? If you choose the midpoints, you end up with the same value, 1, 1, 2 over 3, okay? This is the way we can evaluate the definite integral. Simply, we are taking the limit as n goes to infinity of Rn or Ln or any other sample points or kind of approximation. That is what we mean by definite integral. What is next? Now, how to evaluate some integrals involving functions by considering these integrals as areas. Okay, that is our next point. Now, after we define the integral, we saw how to calculate the integral of some functions using definition, and we understand the meaning of integral geometrically. Let us see how to evaluate the integral of some functions using areas. Okay, we said the integral of a function from a to b represent the net area. That is the area above the x-axis plus negative the areas below the x-axis. So that will give the net area. How to calculate the integral using the meaning of the integral geometrically? That's the purpose of this example. Here we have an example that says evaluate from 0 to 3 x minus 1 geometrically. So what should we do? We need to figure out what is the shape of the function between 0 and 3. So this is what we have, something like this. So this is the x-axis and this is the y-axis. Okay? This is the y-axis like this. So let us say this is, for example, 1. This is 2. This is 3. We are interested from 0 to 3. What is the function we have? Our function here, f of x, is equal to x minus 1. If we graph it between 0 and 3, then we have the following. At 0, it will give me minus 1. So this is something like this. At 0, this is 0 and minus 1. Okay? At 1, it will be equal to 0. At 2, it will be equal to 1. If we say that this is equal to 1 and this is equal to 2, then we have like a line segment joining these points. This is up to 0. Then we continue up to 3. So that will give me 3 and 2, something like this. Okay? Up to here. 3 and 2. So this is a line segment. This is the point 3 and the altitude is equal to 2. Now, what is the meaning of the integral geometrically? If we form this triangle here, look here, okay, if we form this triangle here, this is like this, and we call it, for example, area number 1. And we have here area number 2, which is the area below the x-axis and the area above the x-axis. From the definition of integral, we said the integral from 0 to 3 x minus 1 dx is nothing but the areas above, in this case it is a1, minus the area below, which is equal to a2. And you know that this is a simple areas to be evaluated. This is the area of a right triangle, and this is also the area of a right triangle, which is simply a1 will be 1/2 times the base here, which is the length from here to here, that's equal to 2 multiplied by the height. The height also is equal to 2, so this is equal to 2 minus area number 2, which is 1/2 times the base is equal to 1, and clearly the altitude is equal to 1. So the final answer will be equal to, of course, 2 will divide by 2, that will be 1. So I have 2 minus 1/2, which is simply equal to what? Equal to 3/2. Someone can justify this answer by using also the definition of the integral. The limit as n goes to infinity, the summation stuff we have. The summation of what we call the Riemann sum, and then we take the n as n goes to infinity, we evaluate the limit. Okay. What else we have in this exercise? We are discussing different types of functions. Another interesting question is this. 0 to 1. Another interesting one is this. 0 to 1. Radical of 1 minus x squared dx. Okay. This question can be solved using geometry. It can be solved later by something called trigonometric substitution. But for the time being, we need to solve it in terms of areas. So, what is the representation of this function in terms of areas? What is the function we have? We have y equal to square root of 1 minus x squared. That is the function we have. That's the integrand we need to evaluate. It's integral from 0 to 1. If you need to get an idea about the shape, let us square both sides. So we have y squared equal to 1 minus x squared. Okay? So x squared plus y squared will be equal to 1. And clearly this is the graph of a unit circle. We are choosing the positive values of y, non-negative values of y, so that will give me the upper part of the circle. But we are restricting the x from 0 to 1, so clearly the shape of this will be like the following. It is a quarter of a circle. This is x, this is y. Actually, if we let x to be ranging from -1 to 1, so that will give me a semicircle here. If we just graph the whole thing here, that will be the unit circle. But we are restricting ourselves from 0 to 1, so that will be just what? That will be part of the circle, which is actually a quarter of a circle. Okay? So we are cutting first y to be non-negative, so that's the upper part of the circle. Then we are restricting x to be from 0 to 1, so that will give me this portion of the graph of the circle. Okay? This is 0 and 1, and this is 1 and 0. Clearly here we have a circle with radius equal to 1. Center equal to 0, 0. So we can calculate the total area of the circle, and then we divide by 4 in order to get the portion of the graph here. So what is the integral from 0 to 1? Square root of 1 minus x squared dx. That is nothing but the area of the circle, the unit circle, divided by 4. So that is what? Pi times r squared. R is equal to 1, so it's 1 squared. That is the area of the unit circle. Divided by 4, that will give me the area of a quarter of a circle. So that is pi over 4 simply is the final answer for this integral. And now you can make like a conclusion of this. You can write it as a remark if you like. You can use it whenever you need to use it. Okay? So we have the integral now from 0 to r. In general, you can generalize this into the following formula here. From 0 to r, and we have here r squared minus x squared dx, and this will be equal to what? You can do the same trick we did before in order to graph it. You will see that this is also a quarter of a circle, but the radius is equal to r, so the final answer here will be pi r squared divided by 4. The question is, what happened if we let this one to be from minus r to r? Of course, that will be a semicircle. And the area of the semicircle will be by r squared divided by 2. We are getting 1/2 of the area of the circle. Here what we have is 1/4 the area of the circle. Okay, let us see now a third example about evaluating integrals in terms of areas. Okay, we have a function here says if you have f of x equal to 1 minus absolute value of x minus 1, that's defined between 0 and 2. And radical of 9 minus x minus 5 all squared, this is defined for x greater than 2 less than or equal to 8. We need to calculate this integral of the function. We need to integrate, the question says, find the integral from 0 to 8 f of x dx. Now, how to calculate the integral here? By using areas. That's our target of this. So let us try to sketch the graph of the function here. We have the y-axis here, we have the x-axis, something like this. Try to sketch the graph of the function. We have here 1, let us say this is 2, 3, 4, 5, 6, 7, 8. Okay, so this is 1, 2, up to 8 here. 3, 4, 5, 6, and 7. Okay, if we just sketch the piece of the function here, 1 minus absolute value of x minus 1 between 0 and 2. If you substitute 0, for example, here you will get 0. That is 0 minus 1, which is minus 1. Absolute value is 1. 1 minus 1 is 0. If you substitute 1, this will be 1. So let us say this is, for example, equal to 1. This is 1 and 1. And 2 and 0. So this is the function like this. This is the piece of the function between 0 and 2. As we did before, we need to graph now f of x equal to radical 9 minus x minus 5 all squared. If we just let y equal to this, which is square root of 9 minus, what do we have here is x minus 5 all squared. If we square both sides, then we have y squared equal to 9 minus x minus 5 all squared. Taking this to the other side, so we have x minus 5 all squared plus y squared equal to 9. Clearly, this is the equation of a circle. Okay? And the center of that circle will be 5 and 0, and the radius is equal to 3. We are choosing the positive part of y, so y is greater than or equal to 0, the non-negative part of that. So what do we have here actually is a semicircle whose center is 5 and 0. So this is the point here, where is the center? And we need to move like a radius equal to 3. So from 5 we reach 2, and from 5 we reach 8. So basically this is what we have, which is a semicircle. This is just a sketch of the graph. So what does it represent? The integral from 0 to 8 f of x dx. Simply, it will represent the area number 1 here, which is the area of this triangle, and the area of the semicircle we have. Okay? So let us calculate these areas. So the integral from 0 to 8 f of x dx will be equal to, okay, calculating the area of the triangle here, we have the base is equal to 2 and the height is equal to 1. So that is 1/2 times 2 times 1. That's the area of triangle, which is A1. Plus, now what is the area of the semicircle? What is the area of the circle whose radius equal to 3? It's pi r squared. So it is pi times 9. So the half of the circle will be 9 pi divided by 2. So the final answer will be 1/2 times 2, that's equal to 1. So it's 1 plus 9 pi over 2. So this example, these 3 parts of the example, give us an idea between the relationship between the integral and the area under the curve. And simply we said the integral is the net area. So it is the sum of all areas above the x-axis minus the areas below the x-axis. The next point will be talking about the properties of definite integral. Now we'll talk about some nice properties about definite integral. Okay, we have some properties of definite integrals that are seen from definition. We have first the integral from a to b f of x dx. If we need to switch the boundary points, okay, it will be b to a, but we need to keep a minus sign. Okay, this is the first one. The second one, it says if you integrate a function from a point to the same point, okay, the answer will be equal to 0. The third one says if you integrate from a to b c dx, so this is equal to b minus a times c, and these are other properties. The integral of the sum or the difference is the sum or the difference of the integrals. Then we have the integral of constant times f of x. You can take the constant out. If you split the integral from a to c plus c to b, then this is just from a to b f of x dx. Then we have three comparison properties that says if you have f of x is non-negative, then the integral is also non-negative. If you have f of x is greater than or equal to g of x over the interval ab, of course, then the integral of f is also greater than or equal to the integral of g. And finally it says if you have a function bounded between m and capital M, let us say this is the minimum, this is the maximum of the function, then the integral will be bounded between these two numbers. I will say some words about the proof of these statements, but then I will give some exercise. Not the whole thing, but at least some of them. For example, if we need to show that this is equal to 0, what should we do? Always we go back to the definition here. What is the definition of integral? It says the integral is the limit as n goes to infinity, if you remember, and we have here summation I equal to 1 up to n f of xi. This is one form, delta x, if we choose the right endpoints. But if you are integrating from a to a, what will be delta x? Delta x by definition is b minus a divided by n, but a is the same here. B and a are the same. So delta x will be 0. If delta x 0, everything here is 0. If it is 0, then the limit is also equal to 0, so the integral is equal to 0. That's it. That is the proof of this statement. To show 3, which is the integral from a to b c dx, we need to just show that this is equal to b minus a times z. We will apply the definition. Clearly, the definition says the integral from a to b c dx is equal to the limit as n goes to infinity from I equal to 1 up to n f of xi delta x, where we have the following. Where we have delta x is what? Delta x by definition, it's b minus a divided by n. Then, what are the xi's, the sample points here, the right endpoints of each subinterval? This will be a plus I delta x. What is delta x? Delta x is b minus a divided by n. Now, what is the function we have? The function we have here is the constant function, which is c. Now, plugging this in the formula we have upstairs, we get the following integral. A to b of the constant function dx will be equal to what? Now, we have limit as n goes to infinity. We have summation from I equal to 1 up to n. Now, let us go inside. What is f of xi? F of xi, it means you need to substitute these numbers in the function, but the function is always c. So that is only c. Times what? Delta x. What is delta x? Delta x is b minus a divided by n. Now clearly we have c times b minus a has nothing to do with I. Also n has nothing to do with I. So I can take everything here outside the summation. And that will give me the limit as n goes to infinity of c times b minus a all divided by n times the summation from I equal to 1 up to n of 1, isn't it? After we take everything outside, what it remains here is just 1. Now, what is the summation of 1 n times from 1 to n? That is only what? N. So this is limit as n goes to infinity. We have c times b minus a divided by n times the summation of this is equal to n. Now, n will cancel with n, so this is constant. So what is the limit of a constant? Is the constant itself. So it's c times b minus a, which is exactly number 3 here. This is how to show by using the definition. Similar argument will give me 4 up to 6. Okay, for example here, why the integral of the sum or the difference is equal to the sum of the integrals? If you look carefully for the definition, you will see that it is the limit as n goes to infinity, summation of f of xi plus g of xi. But always you can distribute the summation. So it is summation of f plus summation of g. Then, if the limit exists, then for each one, you can distribute also the limit. So it is the limit of the first summation plus the limit of the second summation, and that will end up with the integral plus the integral, similarly for the minus sign. You can do the rest as the same thing. Here the same, we have constant multiple of f of x. If you apply the definition here, you can take the c outside the summation, you can take the c outside the limit, and that will end up with the right-hand side here. I will comment now in the last three before I give you some exercises. The comparison property says, if we have the comparison properties say, if f of x greater than or equal to 0 for all x between a and b, then also the integral will be greater than or equal to. This is very simple, can be seen from the definition. It can be seen from the meaning of the integral. If we said the integrand is non-negative, so the integral of f of x will represent the area under the curve, and the area always non-negative, isn't it? That is by geometry. You can also use the definition to prove it. The second one is so simple from the first one, because if f of x greater than or equal to g of x, what do we have? We will have f of x minus g of x is greater than or equal to what? 0. Then we apply part A. We just take the integral from a to b. So that will give me the integral from a to b, f of x minus g of x, all of this dx is greater than or equal to 0 using part A. Then we apply the properties. We substitute, using the property of the difference here, that will give me a to b f of x dx minus integral from a to b g of x dx is greater than or equal to 0. And finally, what you need to do is just to take this one to the other side. You have the integral of f greater than or equal to integral of g. This is something about the proof of these statements. But how to use them to solve some questions about properties of integrals, that will be done in the following example. To use the properties of definite integrals to solve the following exercise. The exercise here say, evaluate the integral from part A, said, evaluate the integral from pi to pi sine square cosine to the 4 dx. Although we will learn later how to evaluate such integral, but actually here the answer can be taken in few seconds. The answer clearly here is equal to what? The integral from pi to pi, okay, whatever function you gave me here inside, whatever continuous function you gave me here inside dx, this is equal to what? This is equal to 0, okay? Of course, we are assuming in the properties that all integrals exist. So, in this case, we have the integral from pi to pi, from the same limit to the same. So, whatever an integrand here, which is integrable, the answer will be equal to 0. That's the first point. The second one here is talking about properties of integral. Says, rewrite these summations here, the three terms here, as a single term of the form AB f of x dx. We have from minus 2 to 2 f of x dx, 2 to 5 f of x dx, minus 2 to minus 1 f of x dx. We assume that this integral exists for each term here. We need to rewrite them as a single integral. We need to rewrite them as a single integral. Okay. How to rewrite them as a single integral? I recommend you to do the following. Look for the interval given. The minimum point here given is minus 2. Then we have minus 1. And then we have something like 2. Then we have 5. So this is the interval and the key points we have in the integrals. We have from minus 2 to 2, from here to here. This is what we have. This is the first term. Then we have from 2 to 5. And we have from minus 2 to minus 1, something like this. So one idea to do this exercise is the following. What I will do myself, I will split this one into two parts using the properties. So I have minus 2 to 2 is equal to minus 2 to minus 1 f of x dx, okay, plus from minus 1 to 2 f of x dx. That is the first part of the integral. I split this one into two parts. This is the first and this is the second. The summation here, according to the properties, will give me from minus 2 to 2. Plus, the second one says from 2 to 5, f of x dx minus the last one is minus 2 to minus 1 f of x dx. I said this is one way to solve the exercise. I didn't say that this is the only way we solve the exercise. So this is equal to what? Look here, we have minus 2 to minus 1. This will give me a real number. And it is the same as this real number. So they will cancel each other. We have what? We have 0. Then we have from minus 1 to 2 plus 2 to 5 for the same integrand. So the final answer is, using the property we have, it's from minus 1 to 5 f of x dx. I'm using the property that say, if you integrate from a to c plus c to b, that's the integral from a to b. So from minus 1 to 2 plus 2 to 5 for the same function is minus 1 to 5 f of x dx. That is another use of the properties. A third one here says, given that the integral from 0 to 1 x squared dx is equal to 1/3, use the properties of definite integrals to evaluate the function. Of course, we can evaluate this using the definition. We may use also other techniques to find this, for example, by using later what we call the fundamental theorem of calculus. But here we are using the properties. So how to calculate 0 to 1, 5 minus 6x squared multiplied by dx using the properties of integrals. First, I need to divide this one into 0 to 1, 5 dx minus the integral from 0 to 1 of 6x squared dx. Okay? And then, this is 0 to 1, 5 dx. I can take the constant out, so that is minus 6 times 0 to 1 x squared dx. Now, one of the properties that says from a to b, c dx is b minus a times c. I'm using it here. So that will be what? 1 minus 0, that's equal to 1 times 5. So it is 5 times 1 minus 0. That's the first one. Minus, we have 6 times. Now, this is given for us. Integral from 0 to 1, x squared dx is equal to 1/3. So what is the final answer then? The final answer is 5 times 1, that is 5, minus, we have 6 times 1/3, that's equal to 2. 5 minus 2 is equal to 3. So we used some of these properties to evaluate the integral given here. Now, very interesting question about properties is the comparison properties. Questions about the comparison properties. Specifically the last one. Here we have a nice question that say, use properties of integrals, actually of definite integrals, to verify the inequality without evaluating the integral. We know, or we will know how to evaluate the integral of cosine by using what we call fundamental theorem of calculus. Here he said, no, I need to show the inequality without calculating. I needed to show the inequality without evaluating the definite integral. So how to show this? We have a bound for the integral, okay? Over the whole interval pi/6 to pi/4. So what should I do? Basically to find the answer. What I need to look for is, what is the minimum of this function over the whole interval here? And what is the maximum of this function over the whole interval here? So, what is the maximum, what is the minimum? Looking for the cosine function. Of course, you can use derivatives to find the answer. You can use geometry to find the answer. Okay, I have from pi/6 to pi/4. You know the cosine function. The cosine function between 0 and, let us say, up to pi/2 is something like this. It is a decreasing function up to pi/2. This is pi/2. It is 0 at pi/2. So it's always decreasing between 0 and pi/2. Specifically, if you specify pi/6 and pi/4, it is decreasing. This is at pi/6, and this is pi/4. Okay. This is not exactly the shape, of course, because the partition here is not okay. But if you just do it more carefully, this is what you have. At the end of the day, you need to discover it is decreasing function. But this is the cosine function. Let us say like this. If we assume this is pi/2, for sure, 1/4, 1/2 of this, which is pi over 4 will be here. This is pi over 4, which is 1/2 the distance from here to here, okay? So somewhere here is pi over 6. We don't care about this exactly. What we care about is from pi over 6 up to pi over 4, the function is decreasing. So what is the conclusion if it is decreasing? If it is decreasing, it means the cosine function will be bounded between these two numbers. What are the numbers here? The maximum will appear at pi over 6, and the minimum will appear at pi over 4. So at pi over 4, the cosine will be what? It will be radical 2 over 2. That's cosine 45 degrees. And at pi over 6, that will give me radically 3 over 2. Okay? Here's a common mistake sometimes students do. They said cosine is bounded between -1 and 1. That is true. But we are looking for the minimum and the maximum over the whole interval pi over 6 to pi over 4. Not over the whole real line. We have a specific interval. In that case, we have cosine x is bounded between radical 2 over 2 less than or equal to radical 3 over 2. You can also use calculus techniques you did in previous courses to find the maximum and the minimum over a closed interval, simply by finding the critical points and evaluating at the endpoints, and then you figure out what is the maximum, what is the minimum. This is one way to do it. Here we get the maximum is radical 3 over 2, and the minimum of cosine over the interval is radical 2 over 2. Now, using the comparison property we have, it says then the integral from pi over 6 up to pi over 4 of the cosine of x dx, this will be greater than equal to less than or equal to. Okay. I don't need the graph anymore, so I used it here to find only the maximum and the minimum. Now let us calculate according to the property that says if you have f of x is greater than or equal to small m less than or equal to capital M, then the integral from a to b f of x dx is greater than or equal to less than or equal to what? It is m times b minus a, and here it is small m times b minus a. So what should we do? We need to calculate b minus a. We multiply by this number, b minus a, and multiply by that number. What is pi over 4 minus pi over 6? Pi over 4 minus pi over 6. This is common denominator is 12. So this is 3 pi minus 2 pi. That is equal to pi over 12. Okay? If you take this number now, which is b minus a, you multiply by this number. By these numbers, you get the following. You get a radical 2 times pi divided by 12 by 2. That is 24. Do the same there. You have radical 3 times pi over 24 as desired. This is what we need to show actually in the inequality we did without solving the integral. So now, to summarize what we did, in this section we have the meaning of the integral by definition. We have the meaning of the integral geometrically. Then we use these things to evaluate integrals either by the algebraic way, which is the definition by taking limits of the summation, or using the geometry. And finally, we discuss some properties of definite integrals, and we use them to solve some examples about properties of definite integrals. That is the end of the part which is called definite integrals. Definite integrals. That's it.